Welcome to EPIC Conference. My name is Rodolfo Perissinotto. I'm a researcher from Sub-Project 1, and in this video I'm presenting some new results regarding the effects of viscosity on the flow behavior in an ESP impeller, a comparison between water and mineral oil. So the presentation is divided into 4 parts. We have firstly the introduction, then the revision from topics covered in previous editions of EPIC Conference. Then I'm presenting the new results regarding the influence of viscosity on the flow dynamics and a comparison between water results and mineral oil results. And finally, we are going to close the section with a conclusion. The motivation for Sub-Project 1 is the electrical submersible pump, because the pump performance depends on the flow behavior inside the impeller, for example. In the operation in real applications in the petroleum industry, multiphase flow occurs inside the pump, with presence of oil and water, for example, which leads to the formation of emulsions. And these emulsions increase the effective viscosity and decrease the pump performance. So this leads to an unstable operation and a reduced service life, which are problems for the petroleum industry in the daily life of oil production. In this context, we intend to use the particle image velocimetry, or PIV, to bring new insights about the fluid inside the pump, and then through these measurements made with PIV, we can, for example, investigate the energy dissipation, slip velocity, drop dynamics, turbulence levels, among other quantities inside the pump. And this is translated as improvements on correlations and models, validation of numerical simulations, and other applications such as optimize production, increase efficiency of the pumps, and support the creation of unipeller designs in a long-term application, for example. So this is the whole context of using visualization methods to understand the flow inside the pump. And we do it by using a laser to illuminate the flow. Then we acquire from 500 to 6,000 pairs of images. And these images are more or less like these ones here, okay? So raw images where we can see the fluid and the particles, the tracer particles added to the fluids. And then we process these images to obtain fields of ensemble average velocities in different references, for example, relative velocity or absolute velocity. Okay, so now I'm gonna move on to recapitulation of the other editions of EPIC Conference, because this Sub-Project 1 started in 2019, in the first year of EPIC. And in that time, we were evaluating some studies, some previous studies from literature that motivated our sub-projects. We were also telling you how the development of the transparent pump prototype was going. So this was the main subjects of first EPIC conference. We were still manufacturing the pump. Then in 2020, we reported the assembly of our new experimental facility where the new pump was mounted, and the purchase and installation processes of the new PIV system. This occurred during the pandemic, so we had this online version of second EPIC conference. Then after the pandemic, we had the first results presented in 2021 in the third EPIC conference. And in that time, we were visualizing the oil-water emulsions inside the pump using a high-speed camera without the laser. And the laser was then used in 2022, last year, where we reported some results from PIV tests with water flow. And we were also analyzing the influence of the continuous phase on the dispersed phase. So these are some examples of results presented last year. Okay. and also these ones, these velocity vectors, and this influence, this relationship between continuous and dispersed phases. And now finally we have some new results here in fifth EPIC conference, where we had some new tests using PIV applied to mineral oil flow. And in this case we can better understand the influence of viscosity on the flow dynamics, as we can see here on the left in these flow fields, these velocity fields, as a function of the oil flow rate. So here on the right we can also see a graph showing how the pump head is affected by the viscosity. So these are curves plotted from real data, okay, real performance data acquired during our new experiments conducted in the last months. So we are now working with mineral oil with a viscosity of 15 centipoise, and we can see that as the flow rate increases, the streamlines and also the magnitudes of the relative and the absolute velocities are changing. Okay, we can see differences here on the left inside the impeller, where we analyze the relative velocity, and also here inside the volute diffuser, where we can see the absolute velocity as well. Turbulence also changes as a function of the flow rate for the two different rotational speeds analyzed, and we can see here contour plots of the turbulent kinetic energy calculated from velocity fluctuations inside the impeller. And here on the right we can see a first comparison between water and oil, where it is possible to observe that the lowest turbulence occurs at the best efficiency point, and the highest one occurs at the shut-off or open flow conditions. But also it's possible to note that the turbulence related to the oil flow is much higher than the turbulence associated with the water flow. Now let's have a look at this comparison between water and oil more closely. We start with the velocity fields next to the shut-off condition, 10% of the flow rate corresponding to the BEP. And now we can compare the water velocity fields and the oil velocity fields. At a first glance, there are no much evident differences, but when we look at the streamlines, we can see that these differences actually exist. For water, vortices are formed on the left side of the impeller, and then for the oil flow, these vortices change and their position go to the right side. Turbulent kinetic energy, on the other hand, is very similar independently on the flow or the fluid analyzed. Now, moving on to the best efficiency point, we can see again that the velocity fields are very similar, at least at a first glance, but we can see that the streamlines reveal different profiles or different flow shapes inside the channels. Water is a more flat profile, while oil has this more parabolic profile. And we can see this trend by comparing, for example, this channel here that I'm pointing in the video. For water, we can see that the whole channel is occupied by the flow. When we look at the oil, we can see that the streamlines are more concentrated here in the vicinity of the pressure blade, and in the vicinity of the suction blade there is a detachment of the boundary layers. Turbulent kinetic energy is also different depending on the viscosity. We can see that the oil has a more significant turbulent kinetic energy than the water flow. And this is related to more intense fluctuations that occur even at the best efficiency point. This is an indication of instabilities that require a deep analysis, which we are working on now. Now, to conclude, we can move on to the open flow condition, which is basically 1.6 times the best efficiency point. And again, looking at the vectors at a first glance, we cannot see much difference, but this difference exists, and the streamlines help us to identify or to detect these differences, these divergences between water and oil because of viscosity. For example, if we have a look at this channel here for the water flow, we can see that the streamlines reveal a very intense or a very evident, a very clear deviation of the flow toward the suction blade. But this doesn't happen for the oil flow. In the oil flow, the streamlines deviate less than in the water case. Uh, in the oil flow, the deviations are more slight. So this happens to the other channels as well. And we have also the differences in the magnitudes of the velocities. For example, here the values go up to 2.4 and here to 1.8 meters per second. So there is a difference regarding the intensity of the velocity vectors as well, which is related to the flow rate in which water and oil reach the open flow condition. These flow rates are different because the performance curves of water are different from the performance curves of the oil flow as well. Turbulent kinetic energy is also different, especially regarding the positions or the regions inside the impeller in which turbulence is more relevant. We can see that oil presents a higher turbulence associated with higher velocity fluctuations, and this is an indication of instabilities or indication of larger structures inside the impeller which are being detected by the PIV measurements, and we are now working on this analysis, more deep analysis of these details using another data set from our PIV tests. So, in summary, Subproject 1 analyzed the water flow using PIV in 2022 and 2023, and now we have as plans for 2024 continue studying the oil flow using also the PIV method, but also expanding our study to the oil-water emulsion, in this case working with a two-phase mixture inside the ESP impeller, also with a focus on the flow dynamics, slip velocity, and influence of one phase on each other. In this case, we are using a PIV plus PTV tool. I presented this tool to you in the last workshop in May 2023, and we are also working on this other subject or other topic of our sub-project, but unfortunately I don't have enough time to present this tool and our first results regarding the two-phase flow, but it's something that we will continue working with in the next year. And to conclude this presentation, I'd like to present to you some scientific publications. We have now 3 papers and 1 thesis under development, and other 17 items submitted or accepted or published, as you can see in this list here, okay, in journals, conferences, and also this other slide with more publications from 2022 and 2021. So we have a lot of material available to continue these discussions here. And I'd like to finish with the acknowledgements. I'd like to thank you all for uh, listening to me and watching this video. And I'm also very grateful to our university, the sponsor company, the sponsor foundation, and the research centers as well. Thank you and bye.